Hi everybody, this is the Math 31 optimization review. This is question 16. This question is very nearly identical to the one that we just did. Question 15, if you're doing this systematically here. The difference between this one is that this is now referring to cost, but cost is going to be directly related to surface area here. Okay, so again, here's our can, here's our radius, and here's our height. The limiting feature here is that we know that the volume is 800. So 800 is going to be pi r squared times height. Now, what we are trying to do here is minimize cost. Now, cost is based on the amount of material that we're using. And what we're told in this case here is that the cost of the pieces that we put on the end are 1.4 times the stuff that we put around the side here. Now, we don't know how much that is. Let's just say, for argument's sake, that the stuff that we put along the side here costs K dollars. Let's say this is K dollars per centimeter squared, which means up top here, this is going to be 1.4 K dollars per centimeter squared. Okay? So then what we're going to do here is this will be 1.4 K times 2 pi r squared. That's how much money we're going to spend on the top and the bottom, plus K 2 pi r squared h. Sorry, not 2 pi r squared, just 2 pi r h. Okay, so that's how cost is going to work here. I want to get rid of one of the variables here, but what makes this a little bit more difficult here is everybody, K is not a variable. K in this case would be a constant. So this really does look very similar to the previous question. I'm going to divide 800 by pi r squared to get h. That's what I'm going to substitute in. So now C is going to equal, well, I'm going to simplify this just a little bit. This will be, what is it? It's going to be 2.8 K pi r squared plus, now I'm going to plug in 800 in for h. What do we got here? The pi and the r are going to cancel, so this is going to end up being 1600 K all over r. And I'm just going to double check that that's actually correct there, because I did that kind of in a hurry, and no, that looks right here. So now we take the derivative of cost, which will be 5.6 K pi r minus 1600 K over r squared. Okay, there's our derivative. Now I'm optimizing this. I'm going to set this equal to 0, so this will become 5.6 K pi r equals 1600 K over r squared. Pull up the r squared, becomes r cubed. Now notice the k's are going to cancel. And I'm going to bring that 5.6 pi over, so r cubed is going to equal 1600 over 5.6 pi r. Oh, sorry, not pi r, but 5.6 pi. Okay, so now r will equal the cube root of 1600 over 5.6 pi. And like in the previous questions, so there's really no reason why we shouldn't go through and actually evaluate that. That will be the cube root of 1600 divided by 5.6 pi. And to the nearest tenth, that's going to be 4.5 centimeters. We want to know, it says here, determine the dimensions that minimize the cost here. So there's r. If I want to get h, I got to go back to this expression way back here. That's 800 over pi r squared. And so h will equal 800 divided by pi times the radius squared. And so that is going to be roughly 12.6 centimeters. And there you go. Those are the dimensions of the can related to a minimum cost of production.